This conference will now be recorded.
All right, Mohammed.
Sure. So let me try to share the screen. Um, okay, can you confirm that you see the slides? I will move
Yes.
this.
Yeah, we can see him.
Okay, perfect.
So confirmed.
Okay, so yeah, welcome everybody. This is a follow-up on what we had on the OCP Regional Summit, and basically this is joint work with Thomas Fossati and Simon Frost from ARM. And I would like to first clarify the goals of what we want to achieve via this talk, because this might not be clear to everybody, because typically the talks are about the OCP projects and so on. So I just want to clarify that the goal here is to formally verify and to see if there is an interest in formally verifying the OCP protocols and using our approach that we have used. And the just to say it straightforward, that people are not surprised. So I haven't yet explored the OCP protocols in details, and that's why I will use our recent work, which I just mentioned, with joint work with Thomas Fossati and Simon Frost from ARM. And there I will take Intel TTX as one specific example for this, to demonstrate how this approach can be used. And of course, the approach is usable for different protocols of attestation, because it is also of interest. And the high level idea is that basically we want open source software stacks, and then verify these software stacks, and then one layer above that, the verification software, because of course the verification artifacts, they are also software, and they can also have bugs. And the idea there is that we also have them open source, so people can look at that, these artifacts, check them, analyze them, and then see and get the guarantees, so we can have a fully trusted verification framework. So with that, and feel free to interrupt me at any point of time. So because it will be a bit technology based, just feel free if something is not clear, or something you want more clarifications on that. So just feel free to interrupt me. I would like to start by introducing some of the terms that are important for understanding the approach, or why we take this approach. The problem statement, introducing the confidential computing attestation, and so on, sometimes in relation to that specific scenario, and then the approach and the challenges of the verification that we faced, and then summarize with a small demo of how the artifacts work for Intel TDX. Right. So confidential computing, basically the core idea here is that, imagine that you are, let's say, the CEO of some company. You want to offload all the problems of hardware and software up to the cloud. And then what you do is basically you want to run your data of your company, offload this workload or the service that you provide basically to the cloud. And the idea there is that you don't want to manage the software which is underneath, and you don't want to manage the hardware and its problems and the firmware layer underneath, and that somebody else is doing it for you. And that's basically the goal, the idea to achieve this is via the cloud, that somebody else is the management all these resources. And we still want to protect our business logic, so that we can make benefit, nobody else can actually make benefit out of this. And the it might be some health data, some important data that you still want to protect. So not only the code, but also the data might be important. And here is the idea that we do not want to trust this cloud provider, and we want to remove this from the TCP. So that's the basic idea of confidential computing. Attestation, as is familiar to most of you, just to recall so that everyone is on the same page. What do I mean here in this context? Combining all the three entities that I showed, the hardware and software, hardware and firmware layer, software layer on top of that, and the workload, combining them all together as one attester. and just renaming it so that we can talk about it, and the cloud provider as the adversary. The relying party now wants some guarantees that the data and the code inside the attester is protected and it's running on a genuine machine, and that is having the highest level of the security that is required. In this case, a very simplified scenario, just to introduce attestation, it will send an attestation request. It will get back some evidence signed by the testing environment inside this attester, and then it will verify this evidence, considering that, let's say, the verifier is part of this relying party. And then the idea is that after verifying this, only after establishing the trustworthiness of the attester, it will send over the secrets or the sensitive data that might be medical health records or something like that, or financial records and some similar things, or even personal identifiable information. So that's why it's important, and it's the core of confidential computing. Right. With this short introduction, I want to state the three goals that we were looking at in this specific work. They were to, and this basically TEE, the trusted execution environment. These are called the trusted execution environments, the one attester that I showed in this scenario. And there exists the RATS architecture IETF draft, which is now a standard. However, it's not TE agnostic, and we wanted to make it TE agnostic so we can deal with any TEE that we have. And then once we have this TE agnostic architecture, we want to map the real world architectures to this attestation architecture, which also do not exist. And the third and the most important thing is the formal specifications. How do we get the formal, how do we get these protocols verified at a level of abstraction that is as precise as possible and with the adversary model as strong as possible? And I will in this talk specifically focus on formal specs since that's the most relevant part. So I will not talk about the other two goals that we had. Right. So I will pause for a moment with this problem statement if there are any questions or comments before I go into little bit of details of the approach and describe the properties model and the threat model. So far, so good.
I'll throw something out. I'm going to have to drop after the first half hour, but yes,
Yeah.
verifying the protocol at that high
Mhm.
level is extremely important, but
Mhm.
it's of course not a panacea because when it comes to implementation, there are an infinite number of bugs that people can put in. So I may not
Right.
be around if you do have a chance to answer that, but I just wanted to toss that out. I don't need an answer right now.
Right. Okay. So I think we do not go with so far we have not gone to the actual implementations. We have extracted out these protocols from the Intel's implementation that exists, but then we do not compare one to one against the code updates. So we took a specific version update, and we took that specific version. So Intel is continuously updating that. In that, it was still a very valuable effort that Intel actually acknowledged, and they are collaborating with us on this. But I'm afraid I do not have a very good answer to that for this specific work. But there are other works which actually target the actual implementation and then verify that implementation. So it's possible still.
Okay, thanks very much. That answers my question for now.
Right. Thanks. Okay. So approach, I want to talk about this now, starting from the high level, like when we were dealing with all the solutions now, as I said, one of the goals was TE agnostic. I do not cover that, but that's not very relevant. But from the verification perspective, it makes sense that we have to categorize the solutions into two different categories based on the customizability. Like ARM and RISC-V, they provide the specifications on the basis of one, someone can actually implement their own solutions. And on this side of the spectrum, we have the vendor solution, which we call as the vendor solutions, which is in itself we are not yet very happy with, but this is something that we mean to denote the products which are basically where we have very less customizability in terms of what I can control. For instance, in Intel TDX, there is a component called TDX module, which I cannot really change at the moment, at least. And so there are fixed components within these, and we have very less customizability in this side, and more customizability in this side where we have specs. One can build its own solution, implementation solution on top of that, and have a variety of implementations which use the same starting point specifications. And that's the reason why we call it lead architecture lead solutions. So a number of solutions will be basically built on top of this. And there is not a clear boundary between what needs these solutions, or what distinguishes between. Here there is a clear boundary. I would say the names can be a bit misleading because here ARM is also a vendor which is providing these specifications. So it's specification vendor in a sense. And these solutions actually also have a starting solution which might be which is intellectual property, but they also start somewhere. But here there's a clear distinction if you see like the Intel, AMD, and IBM solutions versus this. And then we wanted to segregate that from verification perspective, because here we verify the specifications, here we verify the actual product which exists. And frameworks which is not very relevant to OCP at the moment. So this is building on top of these to provide a complete solution. For instance, Scone is one that we verified, and Grameen, Microsoft Azure Attestation, Verizon, and many other projects basically use these starting points. For instance, Intel provides the primitives on the basis of which they build their complete framework, starting from the relying party up to the cloud, so that one can verify the whole chain of trust. So this is the core idea, and as I said, I will focus specifically on Intel TDX and describing this to the approach. Here we have the three solutions that I just described, or the three categories. And the idea of our approach is that first we remove the TEE specific parts, map it to an architecture which is independent of the, or agnostic to the TEE. So even if it's a architecture lead solution or vendor solution, it maps to the same terminology, so we can basically compare and contrast them. We can argue about them, deal with them on the basis of a same technology, the same terminology. And then we divide that into three different parts or phases. Provisioning, starting from where the hardware was provisioned with a secret. Initialization, when the initial setup part where the protocol is going to run, and the attestation protocol, which is the actual protocol in the runtime. So with that, these three phases combined together, we want to make, the second step is to make a formal model out of that, all the phases, and combine together and verify some specific properties. Properties here mean the goals which we want to achieve from that specific protocol. It might be secrecy, authentication specifically is important from attestation perspective, integrity, that the data is not modified, and so on. And formal model always has some assumptions. We explicitly specify that the model is based on these specific assumptions. If they are broken by the implementation, then the proof does not hold. And based on these assumptions, we have a formal proof that the formal model satisfies these specific properties. Right. So the novelty in this specific work is that although it do not describe CCA, but still it's the first formal verification and analysis of attestation in its group. RISC-V specifications do not exist yet. According to the latest discussion, they said that it will be in the third quadrant of this year that we will have something. So we started with this CCA. And in this category, we have TDX, which is something that I will talk about. We had a previous work on where we actually verified TDX a couple of years ago when it was announced based on the specifications. And compared to that model, basically the model that we have now is has a lot more details. We have the initialization phase, which was not there. We model the measurements which are taken from the attester as variables. In that model, basically we had them as constant, very simplified model. And comparing the very formal verification time here, for example, to give a rough idea of the complexity of our model compared to the previous model, this is just a rough figure to compare the two models, that it's roughly takes 376 times more to verify, which gives a rough idea of the level of details that it has compared to the previous version that we had a couple of years ago. Okay, and this has been, as I said, very useful for both ARM and Intel. It provides the formal foundation for fine-grained reasoning on different things, because it's the real core thing on which the whole confidential computing is based. And then the idea, it goes to the framework part, where the Barkhausen Institute at Dresden and ARM we are collaborating together to verify the reasoning for remote attestation combined with the TLS protocol. And Intel contacted us that they found it very interesting, and they found that they wanted to have the virtual TPM solution for the trust domain verified in a similar way we verified the Intel TDX, and that's what we are also working on. So these artifacts basically provide the formal foundation for that as well. Okay, so unless there are any questions or comments, so I will describe now what formal methods are at a high level. They are basically mathematical techniques, and what they actually do is they guarantee that the model satisfies a specific set of requirements or goals which we have set for the system. And at a high level, we can say that the system satisfies a specific property. So the requirements are converted into a property, and the system satisfies that. And in this specific context, which we are discussing the protocols, a protocol in parallel to an adversary, both executing together, should satisfy the specific property. And so this basically represents the three things that one needs in order to verify the property. So first one, the protocol that we want to verify, then what is the adversary model for that, and then what properties are of interest for the system. And I will quickly just show one conceptual diagram to show you like the systems that, for example, OCP projects has. They in order to verify, one has to create an abstract model of the system. These projects, of course, have some specific requirements that they have to meet. For example, if it's a protocol, it could be confidentiality, integrity, and so on. And so we formalize that in terms of properties. This is what we can then verify, so that the abstract model created from this system verifies satisfies this specific property. So this is then the goal of the system of the verification, that to see that the abstract model that we have created satisfies this specific set of properties that we have designed for the system. Okay, so now the three things that I described, properties, model, and the threat model or the adversary model, I will now describe each of them in more detail, and to clarify like what do they what do they mean for in general for the approach, and specifically for TDX. Question? Okay, so I heard a noise. Okay. Um, so the this is the figure that I previously showed. Attestation request, evidence, and secrets sent by the relying party. what we are interested in these kind of protocols specifically is confidentiality or the secrecy of these secrets. Of course, we do not want these secrets to be leaked to the adversary, which in this case is this cloud provider, and in the plain text. And secondly, integrity, which is specifically for this evidence which is transported from the attester to the relying party. This should not be modified. So this is the integrity property. Authentication is very important in this context because the relying party needs to be sure that it's talking to an attester which it thinks it is talking to. So that basically is the origin of this evidence. Freshness is very important, that the attester cannot replay this evidence which was generated, for example, at a previous point of time. And it might happen that the cloud provider might change the state of the attester, and if this replay attack is not avoided, then it might the cloud provider might change the state of the attester and send over the old evidence. So freshness of the evidence is very important. And finally, with these set of properties or the goals that we were interested in, we did some sanity checks on the formal model that we created, just to be sure that everything is working fine and everything is as expected. We broke some protocol places at various points of time, and so we performed these checks just to be sure that the protocol works as intended, or our model basically is what we intended to model. Right. I will now describe a little bit about each of these properties, how or give some high level intuition about how they were formalized in our in the tool. And for confidentiality of the secret, the relying party sends an asymmetric encryption of the secret asymmetrically encrypted with the public key of generated inside this attester, which is the public of TDK, trust domain key. And then intuitively the idea is that I want to ensure, can the adversary in between this channel, can it obtain the secret in the plain text or not? And that I can from moving from this intuition to the formalization, I can think of it as a reachability property. And I ask the tool, okay, can I, for this given protocol, for this given adversary, can I reach a state in which this secret is available to the adversary in the plain text? So this is the intuition of that property, and if the answer is yes, the adversary can obtain it, then this property of confidentiality is broken, otherwise not. Okay. um, the second property, integrity of the evidence. And I'm not sure if I said it before, but the motivation of this is that it contains the attester, it contains the identity fields as well as the nonce, to avoid freshness, to avoid the replay attacks. And that's why it's important that it's not modified, so that its identity is preserved. And the idea there is that if now intuitively I can think of it as, okay, so I have a message accepted at the end of this relying party, and message sent from this attester, because I'm talking about the evidence. So evidence, it generated evidence sent over to the relying party. And what I want to ensure is that if I have a message accepted at this relying party, there should be a message sent by the attester. So this is the overall high level idea or the intuition. And now moving a little bit towards formalization, how can I think of it at um, formal, in a formal way, is the correspondence assertions. High level idea is that I have some variables of agreement, which are basically these identity fields or the nonces and the specific claims generated by this attester. And I want to ensure, as I said, that for message accepted at the relying party, these variables are in agreement with what the attester said. So it's kind of a over the observing over both of these and observing that whether they changed in between transport or not. And in terms of this, in terms of modeling, they are represented via events. We have a message accepted event at in the relying party module and the message sent event in the attester. And the query actually checks that, or we ask the tool to actually check that, okay, so given these parameters, let's say these are the claims, identity fields, and nonces and so on, is it the case that if I have a message accepted at the relying party, there was a message sent from the attester with the same set of parameters, that is, these parameters actually agree. Okay, so there is a if condition here that if a message was accepted, it needs to be checked that what happens in the case when no message was accepted, or a protocol never actually accepts a message. So in this case, if a protocol never accepts a message, this query will still be true. And then it's, sorry, question? Okay. Um, and then the idea is that if I have no message accepted, it will still say that the query is true, but I do not have integrity because the relying party never accepted a message. So in order to do this, what we do is basically we check the reachability of message accepted, that the protocol that we modeled has at least one path in the system which leads to a message being accepted. And then this property will give a right answer, that is, if a message was accepted, we ensure via this, then a message was sent by the attester with the same parameters. Okay, I will again pause for a few seconds in order to see if there are any questions or if any comments on this, or should I proceed?
Yeah, I was wondering
Sure.
the confidentiality of secret. What secret is going between the relying party and the attester? What needs confidentiality protection in that case?
I see. So this is basically going back to this figure. This was at the end of the verification of the evidence. It can be any secret. So, for example, going back to the example of the CEO, for example, ensuring that the service is correct, that I am communicating, or a web service is correct. Um, I can now upload my data, uh, health data, finance data, or something like
Oh,
that
so
to the.
this has nothing to do with attestation. It's just once the
Yeah,
attestation
yeah.
is successful, then you send whatever was
Successful. Yeah.
protected. Okay, got it, got it. Thank you.
Absolutely, absolutely. Yeah. So sorry, I should have clarified that. So it's after the evidence is here verified, it's one specific application in which it can send over some specific secrets. So if it is the case, then we want to ensure that the channel that it has created with that attester is secure or confidential, to be more precise. So, of course, you can think of it outside of the attestation goal. So we just verified it to be sure that for these, we can take care of these specific applications also. Okay. With integrity, there is a problem, as I mentioned before. The property that we just I just intuitively explained or formalized does not take care of the freshness. The reason is that all it said was if a message is accepted, there is a message sent by somebody. So with these same parameters. And that somebody part basically we will take care of in the authentication property. But let's first see what's the freshness part. If the query only checks that for so for a message accepted, there was a message sent, then there can be another message accepted for which there is still the same message sent, and now the query will still be true. So it does not detect that multiple messages can be accepted for the same message sent, which in context of attestation is that, as I said before, that the evidence attester, the evidence generated by the attester, the cloud provider can actually change the state of the attester, and it cannot recognize that it's changed because it can replay the same evidence over to the relying party. So what we actually want is this kind of scenario, that for each, so this abbreviating just to save some space. So message, for each message accepted, there is a corresponding message sent. So injective basically relationship, that for each message accepted, there is a corresponding message sent. This is the scenario that we want to model. And with this intuition, the idea is that this for in the query, I can just change this event to injective event, which will then take care of this correspondenceness and ensure that it's one-to-one correspondence with the specific message sent for each message accepted. And so it avoids these replay attacks. And once again, as before, I need to ensure that this message accepted is actually reachable, for the same reason, because the query is saying if a message is accepted, there was a corresponding message sent before. Okay, so I will again pause for a few seconds to see if there is any question or comment before I go to the threat model. Okay, sounds good. Okay, so before threat model, I talk about the model here. Okay, many specifications were not available at the moment we were formalizing, and still they are not available. The idea is to not to wait till all the details are available or everything is available. So basically the idea is to integrate formal methods as soon as possible within the design phase, so that the design team design and the proof evolves in parallel, and that leads to a better design which is actually easily verifiable and is verified to be correct. However, we filled in some of the details which were not available in the specifications, and because I said I'm focusing on TDX for this presentation, so TDX hardware was not available and it's not available yet. So what we did is that we based on our knowledge or experience or experiments with SGX, its previous version, and the DCAP library that its TDX is also reusing. So based on our knowledge and experiments, we basically filled in some of the details in these specifications. And we had a number of discussions then with the TDX architects, a principal engineer at Intel, in order to fill as far details as we can. And the rest are assumed to be secure. So we provide no guarantees, of course, because this is, as I said, verification is only checking that the model satisfies the properties under these assumptions. If the model does not have these specific details, so we cannot do anything with that. We can make it, we can try to make it as generic as possible, which we did for the inputs. But other than that, if there is nothing corresponding to a specific implementation in the model, we cannot provide any proofs. However, we release our code bases online, so Intel and others, of course, can build on top of that when more details are available. And this is very important to emphasize that with incomplete specifications, for example, in case of TDX, it's very easy to show attacks. I can show attacks that, okay, so this specification does not exist. I can put in a dummy case where it will actually show me an attack. And this is really easy to show because of under specifications. But what we actually wanted was something to something working, something that we actually wanted to be usable, that is actually proved to be correct, so Intel can base its design on that, and which actually then on the low side actually needs a deeper understanding of the whole thing, that how it works. Right. Proceeding on to the third thing that I said, the threat model. The threat model for symbolic analysis, which is the approach that we have taken, is very strong at this. We say that when two parties are communicating, everything between them is passing through an adversary. So if A sends a data to B, we say that A sends the data to the adversary and the adversary forwards it to B, and similarly in the other direction. So the adversary is in full control of the communication channel, that it can modify this data, it can drop all the packages, all the packets or the messages, and it can create new messages from its own, and so on, use information from one session to the other session, and things like that. And as I said in the beginning, so the measurements from the attester in the previous works, they were used as constants. So we in our work now we have them as variables, and this leads to a very strong threat model where the adversary can actually now change the measurements. And for specifically for TDX, the adversary has full control to create fake TDs. TD is the name for the VM, the Intel's terminology for the virtual machines. And so what this means is basically quote is the specific name for the evidence. So basically this means that the adversary can actually create a fake VM corresponding to in parallel to a genuine VM, and for the fake TD it can get its evidence, and then it can send over to the verifier, which has now the responsibility to actually check that which one is fake and which one is the real one. And we explicitly mention the assumptions, what assumptions are required for the proof to work. And I will demo it soon. I am about to be, which time? Okay. So with the final thing about the challenges, so the TDX specs were around 1500 pages. So it's basically, I mean, it's the total length of these specs. It's not only about attestation, but the reason I write here is that somehow, as I said, for having a working model, we need to understand the other parts of how things are coming from other modules and so on. And it's really then important to get an understanding of all of the overall picture of the thing, and to make a complete model. And other than these specifications, it inherits specifications from its previous version, which was a process-based version, SCX, as it still reuses many parts, the coding enclave and so on, specific enclaves. And the software development manual for SGX is itself alone is of 5,000 pages. So it was quite a task to try to actually build a complete model of this. And the specs were in natural language, the one released by Intel, which are naturally ambiguous. One can interpret in many different ways, and incomplete, as I said, and even contradicting with the specifications. And what was problematic for us was that the Intel kept updating the specifications on the same link, which is by link I mean the web page for which a spec was uploaded. So Intel would update the specs on the same link, and then one cannot find the old ones to see what has actually changed and how the revision has gone, and the previous versions were actually not maintained. And then what, so these were from the specification challenges. Now we also had a look at the code that Intel released, and to see, as somebody pointed out in the beginning, like what is the implementation? because the implementation is the important thing that we actually want to verify. And we found that the comments in code were also inconsistent with the specifications. And not only that, I do not mention here, but the code itself is also inconsistent. For instance, a specific example is that of um, user data, where Intel claims something else in the specifications, and in the code we found something else. And precise model of the adversary is very important, and that was one of the challenges at the symbolic level. How do we model it very precisely with the measurements as variables, as I described, um, and to keep the formal model as realistic as possible with the actual data formats, and measurements as variables, realistic formal model, and then some user-defined inputs which could have different inputs, different values, as the user might provide different cases, leading to very different implementations. So this is right. I would then switch to the demo. I'm not sure if I shared. I think I shared a window. I need to stop sharing for a moment. Sorry, just a moment. Let me. Uh, my screen. Okay. I think you should be now seeing the code. Right. Um, so okay. So in the meantime, I will just run it and explain what the code is doing actually. Here are the instructions to run it. And then here are the assumptions, as I said, like which specific channels are required to be secure. And for example, adversary has full control to create fake TDs and its code. And then some notations. Okay, so these are the initialization steps, and I would also share in parallel, that would be easier to understand. Um, this figure, which is um, describing all the entities that are there in the protocol, and explaining here the assumptions that we have, which channels are secure. And this guest TD or the user TD basically passes all data through this host VMM, which is insecure, and therefore this channel is also insecure to the trust domain coding enclave. And the channel between here is the verifier, which actually wants to verify this and verify this trust domain or the VM. And that's why this channel is also insecure. And with that, so we have here the initialization phase, the steps for initialization, and then the steps for the attestation protocol, ending at, for instance, this where it has established the trustworthiness of the trust domain. And then as a specific scenario, as somebody also pointed out, like we have uh, data sent from a secret sent to over to with an asymmetric encryption over to the trust domain, and then we check that the trust domain can actually decrypt it, and then at the end that this point of time is actually reachable. Right. With this, so we have then modeled both of these initialization and initialization steps, and then the attestation protocol steps, and described each of the structures, that how it works, uh, up to step 19, and then a specific scenario, if the verification succeeds, then this event is run, which is checking actually the integrity property as I described. So this is representing basically the message accepted as I had in the slides. And then at the very bottom, for example, like okay, or before that, so we have here these queries or the properties that we wanted to verify, the reachability queries, that the reachability of different events at different points of time in the protocol are reachable. And then integrity, injectivity, that means that includes the freshness, basically, because I have here injective events for two different so there are different claims, TCPI claims, TDI, and this user defined data, which is the report data. So this query basically checks that the TCPI claims and R data are integrity protected and fresh, and this query basically checks the remaining claims, which are the TDI claims. And this property is basically the authentication property, that the identity that the trust domain or the VM actually generated inside the key, the public part of the key which it generated inside, and the view of the verifier on this specific key. If both events are reachable, in that case, the key that the VM generated and the key that the verifier thinks that it is communicating with is the same, which is another way of saying that the um, verifier has authentic communication with the trust domain. Right, and then finally the secrecy property, and then for each module, as I described on the this figure. So basically we have here all these entities, one module corresponding to each of these entities. We don't need to model this host VMM since it's a part of the adversary untrusted, and that's why and other than that, we have two different parts for some of the entities because they have also part in the initialization phase. And I will jump to the end of that, the main part where some keys are generated and then sent over to the specific modules. And this is the part where different modules are run in parallel, and this represents the replication of these modules. And the important part to highlight maybe is that this, let me also open the quickly the chain of trust, which might help in explaining. So this is the chain of trust for Intel TDX, and what Intel initially claimed is that this entity PCE is out of the trusted computing base, and then we show it with the help of this tool, basically, that if I so untrusted basically in terms of at the symbolic level means that I can leak out its private key and it should still work, and that's not possible, and we prove it with the help of this by uncommenting this, for example, that so this is C is how do we call it, so the public channel where the adversary has can get information. So if I leak out this private key which I generated, the private signature key, with that I can show then while we take questions, I will then run it again to show you that it will then break the um, integrity properties. Okay, and finally, I think I have, so these are the structures which we modeled. I will not go into details, of course, just to show you at a high level that this TT report is for local attestation and this code is for remote attestation. And so a bunch of things are done. So the high level idea is that the TD claims, a hash is taken over these TD claims, and here are the TDX module, which is the entity which is controlling all these VMs. And basically the hash over these claims is also taken. And then a MAC is taken over all the fields which are in this data structure, including these hashes. And then that MAC is the one which is providing the integrity property. And for the remote attestation, basically it's the signature with the attestation key, which is protecting this code body. We also optimized what should be actually sent as part of the code body. Not all of these claims are required at the verifier end, and that's where we also optimize the attestation protocol. Okay, so it's still running. Okay. Right. Okay. So I think I can then quickly go back to the slides. Okay, to conclude. Okay, so while the simulation ends, so just a couple of slides more. Don't just trust, also verify, and don't just believe, just also argue. Because in the beginning, like I was, okay, so I need to connect the charger. Sorry, just a moment. Okay, I see. Okay. Um, yeah. These are this is basically the reference of our previous work that we had in IEEE Access, and you are very welcome to participate in this. We have these TDX artifacts already available, where we are further refining it and building it open source within the CCC attestation special interest group. And this is the link to the paper, and I think hopefully it might have concluded. Oh, it's still going on. Okay, we can discuss it in the meantime. It concludes, or if you have any questions, we can discuss these while it should hopefully conclude soon. So it's checking the final property, which is the secrecy. So I think single half a minute or minute more.
So I have a question. So this
Sure, please.
environment, in this environment, basically you take all of those specifications and you create these models, right?
Right,
And then in the
right.
simulation, you're running these models and running a bunch of tests and stuff, and that's how you figured out if there's issues. Now, at the beginning, you said that you're trying to make this in a way that is independent from the TEE itself and the
Mhm.
implementation.
Right.
How do you know that your model is complete uh, once you eliminate those dependencies, implementation dependencies? Is there a way to tell?
So far that's so far the artifacts themselves are very dependent on the basically the technologies. But that was a high level overview that if I have, let me quickly jump to the slides. I think it would be. So here the idea was that at least within the groups, I can reuse some parts. For example, if I have for Intel TDX, I can so I can reuse some of the parts at least still for AMD, because it will have a similar chain of trust. Um, of course, it will not have the entities similar to Intel, but it will have some chain of trust. So I can reutilize these parts for this. Um, and similarly, on this side for ARM, I could reutilize some parts for RISC-V in a similar sense that I could reutilize that. But at the moment, we do not have a completely, from the verification perspective, we do not have a completely TE agnostic verification framework. So we provide, or we propose that what we provide can be reused for this group. What we provide here can be used within this group, but not yet for across the group. So because it is specification, it's a product, it's a bit hard. I
So,
hope
so
it.
yeah. So, do you
Sure, please
expect that
go ahead.
you're going to have an independent sort of TEE independent part to the models, and then a small TEE specific part in the future, or do you think you're going to be able to eliminate this TEE specific part entirely?
No, we think that eliminating that TE specific part would be real hard, at least for now. Then we will eliminate so many details. So in order to bring them both at the same level, we will have to eliminate like a lot of details here from the vendor solutions. And currently, it seems to us to be a big challenge. We could use the RATS architecture or the TE agnostic architecture that we propose or have here. But then the point is again that it's so high level, I think, which is also probably what you mentioned, that it's so high level that if I verify that, that provides so weak guarantees that we actually do not want to have this. So what we do is basically some endorsements from this phase can be reused as part of this attestation, some including these certificate chains. Some of the claims can be or the way the claims are modeled actually can be reused across this across both groups, for example. But having completely I mean completely generating the formal specs for both of these categories at the moment, I think it would need a lot of changes currently in the code base that we have.
Okay, got
Probably
it.
we
Thank you.
need to rethink the design itself for that. But it's a very interesting direction in which we are also trying to automate it and make it as reusable as possible.
Hmm. Yeah, thank you.
Okay, so in the meantime, we have the results, which is saying that these are the three reachable queries, reachability queries. They are false. It's a very way of saying that not of this is false, meaning that the actual event is reachable, which was this. And then the injectivity properties are true, meaning that integrity holds and the authentication holds, and then finally the secrecy holds. So if I, for example, read on it, which you can also do it, for example, that with this uncommented, now I will see that the integrity property will actually break. And while it's running, then we can again switch to discussion. Any other comments, thoughts, or questions?
All right. Thanks a lot for your presentation today.
Yeah, yeah,
All right.
Yeah,
We're gonna
thank you.
stop.
That was very interesting.
yeah. Thank